Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here. This is Andrew and Renee. Welcome to the Stack series.
It is wonderful to be here.
Today, we are exploring the multiverse.
Mm-hmm.
And I have to be honest with you right from the start. When most people, myself included, hear that word multiverse, they immediately picture Spider-Man.
Right. The pointing meme.
Exactly. Or, Michelle Yeoh fighting her way through different dimensions with hot dog fingers. It feels very Hollywood.
It certainly has. It's captured the pop culture zeitgeist in a big way, and honestly, that's great for getting people interested in the concept.
Sure.
But today, we're decidedly not talking about fiction. We aren't here to discuss plot devices used to fix continuity errors in comic book movies.
No, we're talking about something that is actually a lot stranger, I think, than fiction. We're talking about a radical rethinking of reality.
A complete rethinking.
And it's being driven by three, very distinct and very serious fields of physics colliding head-on.
That's right. You've got cosmology, specifically the theory of inflation, then you have string theory, and you have quantum mechanics. Three giants.
And all of them, in their own way, are pointing to this same unsettling conclusion.
Unsettling is a good word for it. And I think the most important thing to establish right up front is the sheer scale of what we're discussing.
Right.
When we say multiverse in a physics context, we're not just talking about other worlds in the sense of finding another Earth-like planet a few light years away.
No, this is so much bigger. We are talking about the idea that our entire observable universe, everything we can see with our most powerful telescopes, the James Webb, the Hubble.
Looking back billions of years to the dawn of time.
All of that, the whole show. It might be just a tiny, insignificant bubble in a frothy, infinite sea of other bubbles.
Or perhaps just a single slice of a much larger, infinite mathematical object. It's a concept that, if it's true, it forces us to completely question everything.
Everything we think we know about uniqueness, about our place in the cosmos, and about the very nature of existence itself.
Exactly.
So the mission for our conversation today is really to understand why. Why are these incredibly serious physicists, people like Leonard Susskind, Max Tegmark, Alan Guth, Andre Linde, why are they actually talking about this?
Mm-hmm.
Because looking at it from the outside, for a layperson like me, it just looks a lot like wishful thinking. It looks like, oh, the math got too hard, so let's just say there are infinite universes.
I can absolutely see why it looks that way, but the source material we've been looking at, it suggests it's actually the opposite.
How so?
Many physicists did not want to arrive at the multiverse. They hated the idea.
Really? Why?
But it's messy. It's hard to test. It feels unscientific to them, but they were led there by the equations. The math, in a very real sense, it dragged them there. Sometimes, kicking and screaming.
So if they were dragged there, what was the thing doing the dragging? What's the mystery that's so big it requires infinite universes to solve?
That is the perfect question. And a major driver of this journey, perhaps the biggest one, is something called the fine-tuning problem.
Okay, let's unpack this. The fine-tuning problem. This is the core mystery. So what are we fine-tuning? The radio.
Imagine, if you will, that you're sitting in front of a massive mixing board or a control panel for a very complex machine. This analogy is from Craig Rusbolt, and it's incredibly helpful for visualizing this.
Okay, I'm picturing it. A huge panel, lots of lights, dozens of dials.
Exactly. And each of those dials represents a fundamental constant of nature.
So one dial is labeled strength of gravity. Another is charge of an electron. A third is mass of a proton.
Precisely. The strong nuclear force, the speed of light, the cosmological constant, all the numbers that define the basic rules of our universe.
Right. And you'd think, logically, that if you were building a universe from scratch, you could set those dials to, anything you want.
It seems like you should be able to. Why should gravity be exactly as strong as it is? Why not make it twice as strong? Or half as strong? Why does an electron weigh exactly what it weighs? It all feels
arbitrary.
Completely arbitrary.
Mm-hmm.
But here is the observation, the discovery, that keeps physicists up at night.
Mm-hmm.
If you turn any single one of those dials, any one of them, even a tiny, tiny fraction to the left or right,
what happened?
the universe breaks.
Breaks? What do you mean breaks?
Yeah.
Like it just looks a little different. Trees are purple instead of green.
No, not different. I mean breaks as in game over.
Seriously?
Life becomes impossible.
Yeah.
Chemistry becomes impossible. Stars can't form. The universe either becomes a sterile, empty wasteland, or it collapses back into a black hole in less than a second.
So it's not just that life as we know it is impossible. Any kind of complexity is impossible.
Any kind of structure, any kind of stability, it's just
Yeah.
dead. This is what we mean when we say we live in a just right universe?
We're in the Goldilocks zone. But it's not just for planets being the right distance from a star. It's for the fundamental laws of physics themselves.
That is the perfect way to put it. And to understand just how precarious this is, we need to look at some of the specific numbers. The British astrophysicist Martin Rees, he famously identified 6 of these numbers.
The Rees numbers.
Yes. Let's just look at a few of them to really show you the stakes. Let's start with epsilon.
Epsilon, the Greek letter. And its value in our universe is 0.0007.
Yes.
0.007.
So what is this number controlling? What dial is this?
This number represents the nuclear efficiency of fusion, specifically how efficient stars are at converting hydrogen into helium.
Okay, explain that to me like I'm 5. What does that mean, efficiency?
So inside the sun, you have protons, which are just hydrogen nuclei. 4 of them get smashed together under incredible pressure and heat to form one helium nucleus.
Right.
When they do that, the final helium nucleus weighs a tiny bit less than the 4 protons you started with. A little bit of mass is lost.
And that lost mass, equals
Yeah.
c squared. That's the one. That lost mass is converted into a huge amount of pure energy. That's why the sun shines. And the amount of mass that gets converted to energy in that reaction is exactly 0.7%, or 0.007.
Okay, so 0.007 is the efficiency rating of the sun's engine. So what happens if we mess with that dial? Let's say we turn it down just a notch to 0.006.
If epsilon were 0.006, the nuclear force holding atoms together would be slightly weaker. Protons wouldn't be able to bond to neutrons as effectively. You could never form deuterium, which is heavy hydrogen, and that's the absolute necessary first step to making helium.
So the whole chain reaction that powers stars just never starts.
It never gets off the ground. You'd end up with a universe that is 100% hydrogen forever.
And if you only have hydrogen?
You have no chemistry. You have no water. You have no carbon, no oxygen, no life. Just a boring, cold, dark universe filled with hydrogen gas.
That sounds pretty bad. Okay, so let's turn the dial the other way. Let's crank it up just a hair to 0.008. I mean, it's not a big jump. It's just 1,000th of a difference.
In physics, that 1,000th is a canyon. If epsilon were 0.008, the nuclear force would be so strong, the bonding would be so efficient that fusion would run away with itself.
What do you mean run away?
All of the hydrogen in the entire universe would have fused into helium almost immediately after the Big Bang.
Wait, immediately? Not over billions of years in stars.
Within the first few minutes, boom, all the hydrogen is gone.
But we need hydrogen. It's the H in H2O. It's the fuel for our sun.
Precisely. No hydrogen left means no water. It also means no long-lived, stable stars like our sun. Our sun burns hydrogen slowly, steadily, for billions of years, which gives complex life the time it needs to evolve.
In a 0.008 universe, there's no fuel left for that.
The universe burns itself out before it even gets out of the gate.
Yeah.
All the fuel is used up at the very beginning.
That is unbelievably tight. I mean, it really is a knife's edge. What else is on this cosmic control panel?
Let's look at another big one, omega, represented by the Greek letter A. This is the density parameter of the universe.
Density. So how much stuff is packed into space?
Exactly. It's a measure of the balance between gravity, which is trying to pull all that stuff together, and the initial expansion energy from the Big Bang, which is trying to fling everything apart.
It's a cosmic tug of war.
A perfect analogy. In our universe, this number, omega, is incredibly close to 1. That means the two forces are almost perfectly balanced.
And if they weren't? Let's say gravity was a bit stronger, omega was a bit higher.
If gravity had a slight edge, the universe would have expanded for a while. But then gravity would have taken over, stopped the expansion, and pulled everything back together. It would have collapsed into a big crunch.
Before life had a chance.
Long before. The whole cosmic story would have been over in a few million years, not billions.
Okay, so what if it's the other way? If the expansion's a bit stronger, omega is a little less than 1.
The expansion wins too easily. Everything flies apart so fast that matter never gets a chance to clump together.
So no gravity pulling gas clouds together.
Which means no stars, no galaxies. You just have a cold, thin, ever-expanding mist of particles drifting away from each other forever in the dark.
So we are walking this incredibly thin tightrope between collapsing into a fiery crunch and dispersing into an icy mist.
A very, very thin tightrope. But honestly, Andrew, those are the easy ones to get your head around. The most shocking one, the one that Leonard Susskind literally calls the crisis in physics, is lambda. The cosmological constant.
Lambda. Okay, this is dark energy, right? The energy of empty space.
Yes. This represents the energy density of the vacuum itself. This is the force that we've now observed is causing the expansion of the universe to accelerate.
And I'm looking at the number here in our notes. It says lambda is roughly 10 to the power of minus 122.
Yes, that is a decimal point, followed by 121 zeros and then a 1.
I can't even picture that number. It's so close to zero. Why isn't it just zero?
That is the ultimate question. It is unimaginably small. But here is the kicker. Our best theories, quantum mechanics, suggest this number should be huge. The vacuum of space should be frothing with energy from virtual particles popping in and out of existence.
So the theory predicts a huge number.
A number that is 120 orders of magnitude larger than what we actually measure.
Gee.
It's the single worst prediction in the history of science.
So why is the fact that it's small but not zero a crisis?
Because if this number were just slightly larger, by slightly I mean if you change the 120th decimal place base would expand so incredibly rapidly that structures couldn't form.
What do you mean?
The repulsive force of the vacuum would overwhelm gravity. It would rip gas clouds apart before they could form stars. It would rip galaxies apart. If it were much larger, it might even rip atoms apart. Nothing could ever form.
It's like finding a single, specific, marked grain of sand on all the beaches of the entire Earth. If you pick any other grain, the universe it flies apart.
That's a very apt analogy. It is a level of fine-tuning that is profoundly difficult to explain away as just luck.
I also saw something in the research about to protons. This sounds like a weapon from a sci-fi movie.
It relates to the strong nuclear force, the force that glues atomic nuclei together. We mentioned earlier that protons fuse in stars. But usually a proton won't stick directly to another proton.
Why not?
They both have a positive charge, so they repel each other.
Yeah.
They need neutrons to act as a sort of nuclear glue to hold them together.
Right.
But if the strong nuclear force were just 2% stronger than it is, protons would be able to stick directly to other protons, forming a stable particle called a diproton.
And that would be a bad thing. It sounds more efficient.
Catastrophically efficient. If diprotons were stable, hydrogen fusion wouldn't be a slow, steady burn. It'd be an explosive runaway reaction.
So stars would just blow up.
They would likely blow up almost instantly after forming. Or, even worse, all the hydrogen in the universe might have burned up in the first few minutes of the Big Bang, just like in the epsilon problem we discussed. The entire universe would become helium and nothing else.
It's just one thing after another. And then there's the carbon thing, the Hoyle state. I remember reading about Fred Hoyle. He was a steady state guy, right? He didn't even like the Big Bang Theory.
He was its biggest critic. He actually coined the term Big Bang as a way to mock the theory on a radio show.
So it's ironic he's so central to this.
Incredibly ironic. But he made a profound discovery about carbon. We are, of course, carbon-based life forms. Carbon is absolutely essential. But it turns out that making carbon inside a star is actually really, really hard.
Why is that?
Because to make a carbon nucleus, you have to smash 3 helium nuclei together, pretty much at the same time. But the probability of 3 separate particles hitting each other at the exact same moment is effectively 0.
It's like trying to get 3 people to throw darts and have them all hit the exact same point on the dartboard at the exact same millisecond.
It's just not going to happen. So how do we have carbon? How are we here?
There must be another way.
There is. It happens in a 2-step process. First, 2 helium nuclei merge to form a beryllium nucleus. Then, extremely quickly, a 3rd helium nucleus has to hit that beryllium to make carbon.
Okay, that sounds more plausible.
But there's a problem. That beryllium nucleus is incredibly unstable. It falls apart in a fraction of a second. So for that 3rd helium to hit it and actually stick, there has to be something special about the carbon nucleus.
What's that?
There has to be a resonance, a specific energy level in the carbon-12 nucleus that exactly matches the combined energy of the beryllium and the incoming helium. It has to be a perfect key for a perfect lock.
And Fred Hoyle predicted this lock must exist. He figured this out.
He reverse-engineered it from his own existence. He said, I am here. I am made of carbon. Therefore, this resonance must exist. He calculated the exact energy level it would need to have and told the nuclear physicists at Caltech to go look for it.
And they went and looked for it?
They did, probably thinking he was a bit crazy. And they found it, exactly where he said it would be.
Wow.
Hoyle was a staunch atheist, but this discovery shook him to his core. He later wrote that it looked like a super intellect has monkeyed with physics, as well as with chemistry and biology. He said the numbers seemed too perfect to be an accident.
So we're back to the control panel. We have all these dials, and they are all set to the exact microscopic position needed for us to be here and have this conversation. How do we explain that? Because just saying it's a miracle isn't a scientific explanation.
It's not. And broadly speaking, scientists and philosophers have come up with three possible explanations for this incredible fine-tuning.
Okay, what's number one?
Explanation number one, coincidence. It's a brute fact of our universe. We just got unbelievably astronomically lucky.
Which is deeply unsatisfying.
Extremely unsatisfying to a scientist. It's like walking into a room and finding a pencil balanced perfectly on its sharpened tip. Sure, you could say it could happen by chance, theoretically,
Yeah.
but your immediate reaction wouldn't be, wow, lucky pencil.
No, I'd immediately look for who put it there, or if there was a magnet or some hidden mechanism.
Exactly. You look for an explanation beyond just luck. Which brings us to explanation number two.
Which is?
Design. A creator, a super intellect, fixed the dials. They intentionally set up the universe with these specific values to allow for life.
Which is a perfectly valid theological position, and honestly, looking at these numbers, I can see why people go there. It's a powerful argument.
It is. But it stops being science at that point because you can't test it. You can't put God into a particle accelerator and measure the results. It moves the discussion from physics to metaphysics.
Okay, so if it's not luck and it's not design, what's left for science?
That leads us to explanation number three, the one that keeps the problem within the realm of physics and mathematics. The multiverse.
The idea that there isn't just one control panel.
Precisely. Imagine there isn't just one universe being created. Imagine there are billions upon billions of control panels, or maybe an infinite number of them. And on each one, the dials are just set randomly.
So in most of them, the vast majority, 99.9999%, the settings are wrong.
Yes.
Yeah.
In one universe, gravity is too strong, crunch. In another, the nuclear force is too weak. No SARS. Those universes are born dead, sterile, and dark. There's no one there to observe them or wonder why they're so boring.
But because you have infinite tries, eventually, statistically, you have to get one where all the settings are just right.
And we are in that one.
Yeah.
We find ourselves in a finely tuned universe, not because we are special, but because we physically couldn't exist in any of the others to make an observation.
And this idea has a name. It's called the anthropic principle.
Yes, and this is where things get philosophically interesting.
Okay, let's unpack the anthropic principle, because honestly, every time I hear this, I roll my eyes a little bit. It just feels like a cop-out.
I get that.
It feels like circular logic. The universe is the way it is because we are here to see it, and if it were different, we wouldn't be here.
It sounds like something you say when you just don't have the real answer.
You are in good company. A lot of physicists hate it. They call it giving up. They want a fundamental law that explains why the constants have their values, not just a statistical argument about observation.
So convince me, how is it not a tautology?
The key is to think of it not as an explanation in itself, but as a selection effect. It's a rule about how to properly interpret data when you yourself are part of the data set.
Okay.
The analogy that really helped me, and maybe this will help you, was the royal flush analogy from the research.
Right, the poker hand.
Exactly. Imagine you sit down at a poker table, you deal yourself one hand, 5 cards, and you get a royal flush. Ace, king, queen, jack, 10 of spades. The odds of that are roughly 1 in 650,000.
I would be screaming. I'd think it was a miracle that I was the chosen one, that the universe wanted me to win. Exactly. You would be shocked. You'd think the deck was rigged or it was destiny.
Yeah.
You would ask, why me? Why this specific hand? It would seem to demand an explanation beyond chance.
Right.
But now, change the scenario. Imagine you're in a massive casino. There are 10 million people at 10 million tables, all dealing a hand at the exact same moment.
Okay.
Statistically, it is a near certainty that someone in that room will get a royal flush. In fact, you'd expect about 15 or 16 of them.
It's no longer a miracle. It's just math. It's expected.
Exactly. And each of those 15 people, looking down at their perfect cards, will still feel special. They will still ask, why me? But to the person watching the security cameras of the whole casino, it was inevitable that someone would get that hand.
And the multiverse provides the casino. It provides the 10 million hands.
Precisely. The multiverse provides the probabilistic resources. If you have enough universes, the improbable becomes inevitable. We're simply the winners of the cosmic lottery, looking at our winning ticket and asking, why did I win? The anthropic principle is the reminder that only the winners can ask the question.
Okay, that makes it sit a little better with me. It's not magic. It's just a really, really big sample size.
Right.
Now, I read there are different flavors of this principle, right? It's not just one simple idea.
That's right. There's a spectrum. The most accepted version is the weak anthropic principle, or WP.
WAP.
This is essentially what we just described. It's a statement about observational bias. It says we must find ourselves in a region of space-time or in a universe that is compatible with our existence, because otherwise we wouldn't be here to observe it.
It's like asking, why do I live on a planet with liquid water? Well, because life as we know it needs liquid water to evolve in the first place.
Exactly. It's a selection effect. Then you have the strong anthropic principle, the SAP.
And this one is more controversial.
Much more so. It suggests that the universe must have those properties that allow life to develop at some stage in its history. It almost implies that the emergence of life is a built-in feature of the cosmos, a kind of purpose.
That starts to sound a bit like teleology, the idea that the universe has a goal.
It does, which is why most physicists are very wary of it. It strays from pure mechanism.
And then there's a really trippy one, the participatory anthropic principle. PP.
Ah, PP. This comes from the legendary physicist John Wheeler, the man who coined the terms black hole and wormhole. This is his most speculative and fascinating idea.
He suggested that observers, like us, are necessary to bring the universe into being.
Yes. This connects deeply to the weirdness of quantum mechanics and the idea that nothing is truly real until it is measured or observed. Wheeler took this to its logical extreme.
The old, if a tree falls in the forest and no one is there to hear it, does it make a sound?
He would say, not only does not make a sound, the tree itself might not have been fully real until someone was there to see it. He viewed the entire universe as a self-excited circuit. He drew this famous diagram of a U-shape. At one end is the Big Bang, and at the other end, billions of years later, is an eye looking back.
The universe observing itself.
And in that act of observation, bringing its own past into concrete reality, the observer participates in creating the history of the universe.
Okay, that is a little too metaphysical for me right now. Let's ground this back in the physics.
Okay.
So we have the motivation for the multiverse, which is the fine-tuning problem, and we have a philosophical framework, the anthropic principle. But just needing a multiverse doesn't mean one exists.
Correct. You need a mechanism. You need a theory in physics that actually produces multiple universes.
And we have several candidates. This is where we get into the different levels of the multiverse, a classification system developed by Max Tegmark.
Yes, the cosmologist at MIT. His four-level system is incredibly useful for organizing the madness. So let's start with level I. This is the simplest, least controversial one. It essentially just says the universe is really, really big.
And this idea comes from cosmic inflation, right?
It does. To understand level I, we have to go back to the early 1980s and the work of Alan Guth and later Andre Linde. They were trying to solve some nagging problems with the standard Big Bang theory.
Like the horizon problem and the flatness problem?
Exactly. The universe looked too uniform, too smooth on large scales, and looked too geometrically flat. Inflation solved this by proposing that in the tiniest fraction of a second after the Big Bang, we're talking 10 to the minus 35 seconds, space itself expanded exponentially.
When you say exponentially, you mean faster than the speed of light.
Much, much faster. This doesn't violate relativity, because it's not things in space moving. It's the fabric of space-time itself stretching. It took a region smaller than a proton and blew it up to the size of a grapefruit, and then much, much larger, almost instantly.
And this smoothed everything out, like stretching a wrinkled sheet until it's perfectly flat.
A perfect description. Now, a key prediction of most inflation models is that this process would create a universe that is not just big, but spatially infinite. It just goes on forever.
Okay, so space is infinite, but the speed of light is finite.
And that is the key. Because the speed of light is finite, there is a horizon to what we can see. We can only see light that has had time to reach us since the Big Bang, which is about 13.8 billion years.
This creates our observable universe, or our Hubble volume.
Exactly. It's a sphere centered on us, roughly 92 billion light years in diameter. We can see everything inside it, but we can't see or interact with anything outside it.
So level I is just more of the same stuff, further away, beyond our horizon.
Precisely. It's often called the quilted multiverse. Imagine a vast, infinite patchwork quilt. Each patch is a Hubble volume, just like ours. If space is infinite, then there are an infinite number of these patches out there.
Okay, so it's just more empty space and more galaxies. Why is that considered a multiverse? It sounds like just more universe.
Because of what that infinity implies. It leads to the doppelganger prediction.
This is the part that really freaks me out.
It should. The logic is quite simple, but the conclusion is profound. In our observable universe, in our Hubble volume, there is a finite amount of matter.
Right.
And quantum mechanics tells us that there's only a finite number of ways you can arrange that matter within a defined space. It's a number so large it's practically incomprehensible, but it is finite.
It's like a deck of cards. There are a lot of ways to shuffle a deck, 52 factorial, but it's not an infinite number of ways. Eventually, if you shuffle enough times, you have to repeat a sequence.
That is the perfect analogy. Now, if space is infinite, that means you have an infinite number of Hubble volumes. You have an infinite number of shuffles. If you have a finite number of outcomes and an infinite number of trials, you must get repeats.
It's a mathematical certainty.
It is. So if you go far enough out into space, and it's a very long way, about 10 to the power 29 meters, you will find another Hubble volume that is an identical copy of this one.
Which means there is an identical copy of our galaxy, an identical copy of Earth, and an identical copy of me sitting here in the studio having this exact conversation.
Yes, there is a doppelganger of you. In fact, if space is truly infinite, there are an infinite number of doppelgangers of you. Some are exactly the same. They are saying these exact words right now.
These exact words, that's just strange.
And some are slightly different. Maybe in another Hubble volume, there's a version of you that wore a red shirt today instead of a blue one.
Or one that had tea this morning instead of coffee.
Or one that decided to become a professional mime instead of doing this.
I'm trying to imagine the mime version of this conversation. It would probably be very quiet.
Chuckles. Probably not very successful in an audio format.
But wait, I want to sit with that for a second. The implication. You're saying if I travel far enough, I could meet me. Does this strip away our uniqueness? If there are infinite versions of me, am I just a serial number on a cosmic assembly line?
It's a haunting thought. It's a profound challenge to the ego, to our sense of self. But in this level on multiverse, the important thing to remember is that the laws of physics are the same everywhere.
The control panel is set the same way?
Exactly. Gravity is still gravity. The speed of light is the same. It's just different initial arrangements of matter leading to different outcomes.
Okay, so level I is same rules, different arrangements. But that doesn't solve the fine-tuning problem because the rules are still the same. To get different laws of physics, to explain why the dials are set the way they are, we need to go deeper.
We need to go to level 2. This is eternal inflation. This is where we move from the quilted multiverse to the bubble multiverse.
I love the analogies they use for this. The sources mention Swiss cheese or a pot of boiling water.
Let's use the boiling water analogy. I think it explains the physics best. Imagine the greater universe, the megaverse, if you will, is a massive infinite pot of water on a stove.
Okay.
That water represents the inflationary field, a state of very high energy, rapidly expanding space. In most of the pot, the water is at a rolling boil. It's expanding furiously. That's the state of inflation.
So the whole pot is constantly getting bigger and bigger.
Yes, but in random spots, a bubble forms. Inside that bubble, the water stops boiling and cools down. The energy drops. That sudden drop in energy, that reheating, turns the potential energy of the inflation field into all the matter and radiation we see.
And that moment when the bubble forms and the boiling stops inside it, that's a big bang.
That's a big bang. Our entire observable universe is just one of these bubbles that formed in this vast boiling pot. We live inside a pocket universe.
But the water around our bubble,
The space between the bubbles is still boiling. It's still in that inflationary state, expanding exponentially. This pushes the bubbles apart from each other faster than the speed of light.
so we can never reach another bubble. They're physically isolated from us forever.
Exactly. And the process never stops. That's the eternal part of eternal inflation. Once inflation starts, it's very hard to stop it everywhere at once. It stops in pockets, creating universes like ours. But the space between them keeps growing and creating more space, which in turn generates more bubbles. It is a runaway, self-reproducing multiverse factory that goes on forever.
Now, here's the crucial question. Why is this level 2? How is it different from the infinite quilt of level 1?
Because in these different bubbles, the effective laws of physics can be different.
The dials on the control panel can change from bubble to bubble.
The dials can change. Think of it like water again. Water can exist as a liquid, as solid ice, or as steam. Those are different phases of the same substance, H2O.
Right.
In modern physics, we think of empty space, the vacuum, as a kind of substance. It's a field. And that field can freeze into different stable configurations, different phases.
Phases of nothingness.
It sounds strange, but yes, the vacuum is not truly nothing. It's teeming with potential. And as each bubble universe cools down from the boiling inflationary state, its vacuum can settle into a different phase.
So in one bubble, space might freeze into a phase where the electron is really heavy. In another, it's light.
Exactly. In one bubble, electromagnetism might be incredibly strong. In another, it's weak. In some bubbles, there might be 5 large dimensions of space instead of our 3.
So this is the mechanism that solves the fine-tuning problem. We are just in one of the bubbles where the cosmic water happened to freeze in a way that allows for chemistry, stars, and life.
That's the idea. Eternal inflation creates the casino with all the poker tables. But we still need to know why the laws can be different inside them. What determines the rules of the game at each table? What allows the dials to turn? That brings us to our third major player, string theory.
Ah, string theory. The theory that has promised a theory of everything for decades and has proven, well, we'll get to the controversies later, but for now, give us the basics.
The fundamental idea is that if you could zoom in on any particle, an electron, a quark, a photon, you wouldn't see a point. You would see a tiny, one-dimensional, vibrating loop of energy, a string.
And different vibrations of the string correspond to different particles.
Yes. One vibrational pattern makes the string appear to us as an electron. A different pattern makes it appear as a photon, a third, a quark. It's like the different notes you can play on a violin string. All the particles and forces of nature are just different notes played by these fundamental strings.
That's a beautiful, elegant idea.
It is. But there's a catch. For the mathematics to work, for the theory to be consistent, these strings can't just vibrate in our familiar 3 dimensions of space and one of time.
This is where it gets weird, the extra dimension.
Yes, string theory requires that the universe has 10 or 11 space-time dimensions.
Okay, stop right there. You said 10 dimensions. I am looking around this studio. I see up, down, left, right, forward, back. That's 3. I'm experiencing time, so that's 4. Where are you hiding the other 6? Under the desk?
Chuckles. Not under the desk. They are everywhere, at every single point in space. But they are compactified. That means they are curled up into a tiny, tiny shape, so small that we can't see them or move in them.
Give me an analogy for that. How can a dimension be curled up?
The classic one is a garden hose. If you look at a garden hose from a mile away, it looks like a one-dimensional line. An ant on that hose could only move forward and backward along it.
Right.
But if you walk right up to it and look closely, you see it has a second dimension, a tiny circular dimension. The ant can walk around the circumference of the hose as well as along its length.
Okay, I can picture that.
String theory says that at every point in our 3 big dimensions, there are another 6 or 7 dimensions curled up, like the circumference of that hose, but in much more complex shapes.
And the shape of that curling, it matters.
It matters more than anything. These 6-dimensional shapes are called Tilapio manifolds, and they are incredibly complex. And here's the absolute kicker. There are many, many different ways to fold or curl up these extra dimensions.
How many?
The current estimate is somewhere around 10 to the power of 500.
10 with 500 zeros after it. That is a number so big there aren't enough atoms in the entire observable universe to write it down.
Correct. And the specific shape of those curled up dimensions determines everything about the physics of that universe. It determines how the strings are allowed to vibrate.
So it's like the shape of a musical instrument. The shape of a French horn determines the sound it makes compared to a flute, even if the musician is the same.
An excellent analogy. The shape of the extra dimensions is the instrument. It dictates the notes the strings can play. And those notes are the particles and forces.
So let me see if I get this straight. If you fold the extra dimensions one way, the string vibrates at a frequency that makes it look like an electron with mass x. If you fold it a different way, it vibrates differently and looks like an electron with a totally different mass, y.
Exactly. Or you get a universe with no gravity. Or a universe with 5 types of electrons. Or one where the strong nuclear force is 2% stronger. Each of the 10 to the 500 possible shapes for the extra dimensions corresponds to a different set of dials on our control panel, a different vacuum state.
This collection of all possible universes is what they call the string theory landscape.
Yes, it's a vast theoretical terrain of possibilities. For a long time, physicists like Leonard Susskind were hoping that string theory would have a unique solution. They hoped the math would point to one specific shape, one valley in this landscape, that would explain why our universe is the way it is.
They wanted the theory of everything to predict us uniquely.
They did, but they didn't find one peak, one special valley. They found a discretium, this landscape with 10 to the 500 valleys. Susskind has said he was in a state of crisis at first. He was distraught.
Because it meant string theory couldn't predict anything.
Or so it seemed. But then he and others realized it wasn't a crisis, it was the solution.
Because you combine it with the bubbles from eternal inflation.
You put the 2 ideas together. If you have eternal inflation, which makes an infinite number of bubble universes, and you have the string landscape, which offers 10 to the 500 possible sets of physical laws, you inevitably populate the entire landscape.
Every possible universe exists somewhere in some bubble.
Every physically possible universe. And suddenly, the fact that we live in a universe suitable for life isn't a deep mystery that requires a miracle. It's just geography. We live in one of the rare, fertile valleys in this vast cosmic landscape because we couldn't possibly live on the sterile, hostile peaks.
Okay, so that covers the multiverse of vast distances, level 1, and the multiverse of varied physical laws, level 2. But there's another kind of multiverse that's much closer to home. It's happening right now, right here, level 3, quantum mechanics.
Yes, this is the many worlds interpretation, or MWI, first proposed by a PhD student named Hugh Everett in the 1950s.
And this is the one involving Schrödinger's cat. We have to talk about the cat.
We have to. The famous, unfortunate cat in a box. In the standard Copenhagen interpretation of quantum mechanics, a subatomic particle can exist in a superposition of states. It's both here and there, spinning up and down at the same time. It's just a wave of probability.
Until you measure it.
Right. The act of measurement forces the particle to choose. The wave function collapses into a single definite reality. The radioactive atom in Schrödinger's experiment either decayed or it didn't. The cat is either alive or it's dead.
But Everett was looking at the math, at the Schrödinger equation itself, and said, wait a minute, there's nothing in the math that says it collapses.
That's exactly his insight. He said, why do we add this extra rule, this collapse postulate? Let's just trust the equation. He proposed that the wave function never collapses. Instead, when a measurement is made, the entire universe splits.
So in one branch of reality, the atom decays, the poison is released, and the experimenter opens the box and sees a dead cat.
And in another, completely separate branch of reality, the atom doesn't decay, and the experimenter opens the box to find a perfectly alive cat.
And both of those experimenters and both of those cats are equally real.
Equally real. Every single time a quantum event has multiple possible outcomes, all of them happen, each in its own new branch of the universe. The universe is constantly, ceaselessly branching, creating infinite parallel timelines.
This feels fundamentally different from the bubble universes. The bubbles are incredibly far away in space. This is happening here, in this room.
Right here, right now. As we speak, every time a particle in the air interacts, the world is splitting into countless versions.
I don't feel the split. I feel like one continuous me.
There's a famous exchange about this. A critic asked Everett, if the universe is constantly splitting, why don't I feel it? And Everett supposedly replied, do you feel the motion of the Earth?
Touché. We're spinning at 1,000 miles an hour and hurtling through space, but it feels perfectly still to us.
We don't feel the split because we are part of the system that is splitting. You, the chair you're sitting on, the air in this room, we all split along with it. The version of you in one branch has no awareness of the other.
Now, here is where it gets really interesting and honestly a bit confusing for the people deep in this field. Some physicists, like Yasunori Nomura and Leonard Susskind, have argued that these different multiverse levels, level 1, level 2, and level 3, might actually all be the same thing.
This is a very deep and subtle insight. It connects to another profound idea in physics called the holographic principle. The idea that all the information contained in a volume of space is actually encoded on its boundary surface, like a hologram.
But how can the bubbles far away in space be the same as the quantum splits happening right here? They seem like totally different concepts.
They argue that global space-time might be a redundant concept, that it's all a matter of perspective, of your reference frame. If you are an observer inside one bubble, looking at the quantum probabilities of what might happen next, it looks like the many worlds of level 3.
Okay.
But if you could somehow zoom out and look at the entire mathematical structure of all those possibilities at once, the whole probability space, it would look like the landscape of bubble universes from level 2.
So the multiverse out there and the multiverse in here are just two different mathematical descriptions of the same underlying reality.
That's the proposal. It suggests that the distinction we make between probability space in quantum mechanics and physical space in cosmology might be an illusion. It's a way of unifying these disparate mind-bending ideas into one, even more mind-bending picture.
Okay, we've covered vast distances, bubbling universes, and splitting timelines. But Max Tegmark has one more level for us, level V, and this one makes my brain hurt just thinking about it.
Level 4 is the ultimate ensemble. This is the realm of what he calls the mathematical universe hypothesis, or MUH.
The idea that the universe is math, not just described by it.
Exactly. We're all used to the idea that math describes the universe. We write equations to model gravity to predict the path of a planet. Tegmark takes a radical step further and argues that the universe literally is a mathematical structure.
What does that even mean? The universe is a structure. How can a structure be a place I can live in?
It means that on the most fundamental level, physical existence and mathematical existence are the same thing. Think about a perfect circle. A circle exists mathematically. It has properties like pi. You don't need to build a circle out of wood for the concept of a circle to be real in the world of logic.
Right. It exists as an idea, a form.
Tegmark argues that our physical reality is just a really, really complex version of that circle. It is a mathematical structure so complex that, to the self-aware substructures living inside it, that's us, it feels solid and real.
So if our mathematical structure is real, does that mean that other mathematical structures are real too? Like a universe based on a different kind of geometry? Or one that follows a bizarre 12-dimensional logic?
Yes. That is the core of level 4. Tegmark calls it mathematical democracy. Why should our specific set of equations, our specific mathematical structure, be the only one that gets to be physically real? Who decides that? God. Luck.
He argues no one decides.
Exactly. He argues that all mathematical structures that are logically consistent, that don't contain contradictions, exist physically.
It eliminates the free parameters. It eliminates fine-tuning entirely. You don't have to ask why these laws, because the answer is all laws exist.
We just happen to be a self-aware substructure that evolved inside this particular mathematical object. It's a form of radical Platonism. It's incredibly elegant. In a strange way, it solves the ultimate question of creation by saying everything that can exist does exist.
It's elegant, sure. It's a beautiful idea. But Renee, is it science?
That is the big question.
Yeah.
That is the billion-dollar question.
Yeah.
And that brings us to the skeptics, because we have spent all this time building this towering, magnificent edifice of the multiverse.
Yeah.
But we have to acknowledge that there is a lot of serious pushback from within the physics community.
And the primary criticism is about falsifiability, right? Karl Popper's golden rule of science.
Yes. Karl Popper, the famous philosopher of science, argued that for a theory to be truly scientific, there must be a way to prove it wrong. My theory can't just explain everything. It has to make a specific testable prediction. If I say all swans are white, my theory is scientific because you can go out and look for a black swan. If you find one, my theory is busted.
Right.
But if I say there is a universe beyond our horizon that you can never see, touch, or measure, how can you possibly prove me wrong?
You can't. By its very definition, it's unobservable.
And critics like the science writer John Horgan have called this pseudoscientific bullshit. His words, not mine. He argues that theoretical physics is retreating into a kind of fantasy because the math has become completely detached from experimental observation.
It becomes a matter of faith, not evidence.
Precisely. And there are other more technical problems. There's the measure problem. This one seems to really bug the statisticians and cosmologists working on this.
What's the issue there?
It's a nightmare. If eternal inflation is true, and there are an infinite number of universes, then everything that can happen does happen, and it happens an infinite number of times.
So there are infinite versions of me hosting this conversation, and infinite versions of me who decided to become that mime we talked about.
Exactly. So if you ask a simple question like, what is the probability that Andrew became a mime? Normally you would count the number of mime outcomes and divide by the total number of outcomes. But here you have infinity divided by infinity.
Which is undefined. It's meaningless.
It is mathematical nonsense. And if you can't calculate probabilities, the theory loses all predictive power. If the theory just says everything happens 100% of the time, you can't use it to predict what we should observe. Physicists are working hard to fix this, trying to find a rational way to count the infinite universes, but it remains a very deep, unsolved problem.
That seems like a pretty serious flaw. And then there's the swampland problem you mentioned, which affects string theory.
This is a more technical issue, but it's fascinating. It turns out that string theory works really, really well in a specific type of mathematical space called anti-de Sitter space, or ADS. Imagine a universe with negative curvature, like a saddle or a Pringles chip.
Okay, a Pringles universe. But we don't live in a Pringle.
No. Observations of our universe show that we live in de Sitter space, or DS. It has a slight positive curvature, and it's expanding and accelerating because of dark energy, that tiny lambda value.
So what's the problem?
The problem is, string theory has a devil of a time describing our kind of universe. It's very, very hard to construct a stable, consistent de Sitter universe from string theory. So some physicists, like Cumrun Vafa at Harvard, have argued that perhaps universes like ours reside in the swampland.
Swampland.
It's their term for the set of theories that look consistent on paper, but are actually impossible to realize in a true theory of quantum gravity. They're mathematical mirages.
So the one universe we know exists, our own, might be the one that string theory can't actually explain. That seems awkward.
It's a huge point of tension. If Vafa's right, it could mean that the string theory landscape isn't real, or that the multiverse isn't possible in the way we've been describing, or perhaps our vacuum is only metastable,
Meaning what?
meaning it looks stable, but it's not the true lowest energy state. It's like a ball resting in a shallow dip on the side of a huge hill. It can sit there for a very, very long time, but eventually, with a random quantum fluctuation, it could tunnel through and roll all the way down to the bottom.
And if our universe did that?
The laws of physics would change instantly. It would be the end of everything as we know it. But don't worry, the calculations suggest our universe is stable for trillions upon trillions of years.
Okay, that's a relief. So despite all the skepticism, despite the swampland and the measure problem, are there any ways we could actually test this? Or are we stuck in the realm of philosophy forever?
We aren't completely stuck. There are some potential indirect tests we could look for. We mentioned bubble collisions
There
earlier.
are bruises on the sky.
Exactly. If our bubble universe happened to bump into another bubble early in its history, like two balloons pressing against each other in that boiling pot,
Yeah.
it might have left a permanent mark.
What would that mark look like?
It would probably look like a circular pattern, a disk, in the cosmic microwave background, the afterglow of the Big Bang. It might be a cold spot or a hot spot with a specific temperature profile.
And astronomers have actually found something like that, haven't they? The CMB cold spot?
They have. There is a massive region of the sky that is unusually, inexplicably cold. It really shouldn't be there, according to the standard model of cosmology. Some cosmologists, like Laura Mersini-Houghton, have argued very forcefully that this is the signature of a collision with another universe.
But it's controversial.
Very. Others argue it's just a statistical fluke, or that there's a huge void in the distribution of galaxies in that direction that's causing the effect. But it is, at least, a potential, testable, observational link to the multiverse.
What about other tests?
There's the idea of looking at black holes. If we can ever truly understand the information paradox, how information is preserved when it falls into a black hole, and confirm Stephen Hawking's theory of radiation, it might confirm the holographic principle.
And as we discussed, if the holographic principle holds, it strengthens the mathematical link between the quantum multiverse and the inflationary multiverse.
Exactly. It would lend credence to the whole interconnected structure of these ideas. So we aren't completely flying blind. We are looking for these subtle footprints in the cosmic dark.
As we wrap this up, I want to step back and look at the big picture. Why does this all matter? Why should the person listening to this, driving to work or washing the dishes, care about 10 to the 500 universes or quantum splits?
I think it matters because it frames our entire place in reality. It is the next and perhaps final step in a story that began with Copernicus 500 years ago.
The Great Demotion.
Yes, the continued demotion of humanity's specialness. First, we learned the Earth wasn't the center of the solar system. Then we learned our sun wasn't the center of the galaxy. It was just an average star in the suburbs.
Then our galaxy turned out to be just one of hundreds of billions.
Now, the multiverse suggests that our entire universe, with its unique laws of physics, its specific particles, its three dimensions, is just one random, insignificant speck in a much larger, grander structure.
It makes us feel incredibly small and insignificant.
It does. It can. But I think there's another way to look at it. It also promotes us in a strange way. It highlights the incredible rarity and preciousness of complexity. In this vast, mostly dead multiverse, we exist. We are in that royal flush universe.
We are the rare instance where the universe woke up and started looking at itself.
Exactly. It also marks a huge philosophical shift in what we want from science. It's a debate between what you might call elegant simplicity and messy abundance.
What do you mean by that?
We used to want a theory of everything that was simple and unique, one formula that would explain why things had to be this way. The multiverse offers a different kind of simplicity. The simplicity of everything. You don't need to explain the specific choices if all possible choices are made somewhere.
Messy abundance. I like that phrase. It feels very human, actually. Life is messy. Nature is messy. Why shouldn't the cosmos be?
It does. And I think Tegmark's view, that a theory with no free parameters, like is level 4, is actually simpler than a theory that requires you to specify 20 different constants, is a profound philosophical shift. It trades the complexity of the laws for the complexity of the ensemble.
So what this all means is that we might be living in a reality far bigger, far stranger, and far more crowded than we ever dared to imagine.
And it leaves us with a fascinating and perhaps slightly unnerving final question to ponder. If we are just one of infinite possibilities, what does that say about the value and meaning of the choices we make right here, in this specific branch of the wave function?
That is a question we will have to leave for our listeners to ponder on their own.
It's indeed.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support. And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stack Studios for more informative content, and support us in Patreon. Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.